Okay, this video here is going to be all about thermochemistry. Specifically, we're going to focus on enthalpy and Hess's law. Now, thermochemistry, depending on how far you go in your chemistry career, could be another year's worth of courses just on this particular topic. We're going to very much so just cover the surface of that idea. Okay, and again, we're going to cover enthalpy and Hess's law. Now, thermochemistry is defined as the study of heat changes in chemical or physical processes. And when we're talking about thermochemistry, we're talking about two major parts, the system and the surroundings. The system is where the reaction is taking place. So that is the reaction itself. The surroundings, well, that's everything around the reaction. So everything but the reaction. When you put those two things together, you get the whole, you get the universe. So think about like a picture on maybe the whiteboard in class. The picture itself would be equivalent to the system. Everything else on the board, all of the whiteness around it, that's the surroundings. Now where this brings us is the concept of enthalpy. In the obvious or not so obvious abbreviation for enthalpy is H. And that is actually the heat content of a system at a constant pressure. So we can't measure heat. There's no tool for measuring heat. You think about the way that we measure what we perceive as heat or use synonymously as heat, and we use the thermometer. But a thermometer actually measures temperature, which is the average kinetic energy. Heat is something a little bit different altogether. So instead of measuring heat directly, we have to measure it indirectly through the changes in that enthalpy. So the way that we're going to do that is we're going to actually use delta H, which means a change in enthalpy. And the equation that we're going to use for that is that delta H is equal to the H of the products minus the H of the reactants. We're going to get some type of value for this answer, and usually it's going to be expressed in the unit of kilojoules. A positive delta H value means that we have an endothermic system. It means that in order for the reaction to take place, energy must be provided from the surroundings into the system. A negative delta H value is not a bad thing. It, however, means that the reaction generates heat that must be given back from the reaction, the system, into the surroundings. It is therefore exothermic. Together, when we have this enthalpy problem, we form what's called a thermochemical equation. And this is going to be a balanced chemical equation with the states of matter and the heat energy change as part of the equation. So here's an example of a thermochemical equation, or the type of problem we'd have to be able to do based on the wording here. It says write a thermochemical equation for nitrogen monoxide and oxygen synthesizing nitrogen dioxide. So the word synthesizing is a dead giveaway that we're going to be dealing with a synthesis reaction. Nitrogen monoxide is NO, and that is a gas. To it, we're going to add oxygen, which is one of our Brinkelhoffs, our diatomic elements. And we're going to synthesize nitrogen dioxide, which is also a gas. Now, like any good equation, what we need to do to it in order to proceed is to balance it. Quickly balancing this equation, we get 2 NOs and 2 NO2s. This is going to give us a total of 4 oxygens on each side and a total of 2 nitrogens on each side. Then we need to use a list of thermodynamic properties, or a specific set of constant values for the formations of each of these substances. These values will be provided for you and have been posted to the class website. When we look up the heats of formation of these, we find that nitrogen monoxide has a heat of formation of 90.25 kilojoules per mole, while oxygen is 0 kilojoules per mole. And the reason that it's kilojoules per mole is because, or 0 kilojoules per mole, is that oxygen naturally occurs in this state of matter. NO2 has a heat of formation of 33.18 kilojoules per mole. According to the equation that we looked at on the previous pages, our overall delta H of this equation is going to be equal to the H of the products minus the H of the reactants. So real quickly, remember, the products are over here and the reactants are over here. So now it's simply a matter of doing your multiplication. Our H of products is going to be 2 moles times 33.18, and that is our total products minus our total reactants. Now, we should include oxygen here, so we will. 2 moles times 90.25, and then add to that the 0 from over here. Now a little quick math gets us to 66.36 kilojoules for product side and 180.5 kilojoules for the reactant side. Subtracting these together, we get our total delta H of the system to be negative 114.14 kilojoules. Again, this is not a bad thing. This simply means that when this reaction up here forms, it will actually give off 114.14 kilojoules of heat. It will leave the system and go back into the surroundings and will therefore feel warm. Another equation or law that we need to discuss is that of Hess's law. And this is a picture of Germain Hess. And he worked with different kinds of reactions. And what he noted is that a lot of chemical reactions actually take place in a multitude of steps. And multiple steps come together to form an overall answer, an overall reaction. And so he said in the instances of multiple step problems or multiple step reactions, the sum of all the intermediate steps will result in the total enthalpy. In order to make a problem like this work, however, we need to look at each of the individual steps and often flip the equations to come up with the total enthalpy of the entire system. So here we have an example problem of Hess's law. It says use the thermochemical equation below to determine the enthalpy for the reaction. We'll be trying to determine the enthalpy of this reaction right here, based on these 3 knowns right here. The idea is to cancel out what you don't want in order to get what you do want. We do want to have 1 nitrogen and 2 oxygen molecules on the reactant side and 2 molecules of nitrogen dioxide on the product side. However, if we look at this problem, we don't already have all that stuff, and in fact we have many things canceled out. Well, if we look carefully at the second equation right here, the second equation is the only equation that contains nitrogen dioxide. Nitrogen dioxide needs to be found on the opposite end of the arrow. So what we're going to do is we're going to flip this equation. So we're going to rewrite it. 2 NH3s plus 4 H2Os will yield 2 NO2s plus 7 H2s. That's also going to flip the sign of our reaction to negative 28.5. And this will cause this one to go away. Now, if we were to take a summation right now, we would find that we have on the left side of the arrow 1 N2, 4 H2s, 3 here, 1 here, half of an O2, I'll explain that in class, 2 NH3s, and 4 H2Os. On the product side, we would have 2 NH3s, 1 H2O, 2 NO2s, and 7 H2Os. In order to make this entire problem work, we must multiply this by 4 to get us to cancel out what we're looking for. When we do that, we will find that we get 1N2 plus 3 H2s, that's from the top equation, plus 4 H2s plus 2 O2s plus 2 NH3 plus 4 H2O. And I'm actually running out of space here, so we're going to copy onto the next slide. Okay, so taking what we have there, we also need to form our product side. Now our product side, and to copy that, we'll just go one more page. And we had N2 plus a total of 7 H2s plus a total of 2 O2s plus 2 NH3 plus 4 H2O. That was all, that was all on the reactant side. And on the product side, I'm going to just draw it like that. We have 2 NH3 plus 4 H2O plus 2 NO2 plus 7 H2O. That's 7 H2. So that should be what we have on the other side. Now note that we have 2 NH3 on both sides, here and here. Therefore, they will cancel off. We also have 4 H2O on both sides of the arrow, and 7 H2s on both sides of the arrow. So what we're left with is these following. We have N2, we have 2 O2, and we have 2 NO2. Once everything cancels out in the proper way, we can go back and look at our energy. Well, our energy from our first equation was negative 23 kilojoules. To that, we're going to add 8.7 kilojoules. And to that, we need to multiply that value. We need to multiply that by our 4. So 8.7 times 4 is 34.8. Then we're also going to add negative 28.5. When we add all of these values up, we get a grand total of negative 16.7 kilojoules. All these partial equations yielded this as our final equation. And this is an example of Hess's law.